Next, we are gonna take a look at confidence intervals for population proportions. So when estimating population proportions, usually what you are either going to be given the sample proportion, or you're going to be given the total sample size and the number of successes in that sample. Then you can find your sample proportion denoted by p hat by dividing the number of successes by the total number, total sample size. Now, to find the percentage of failures, that's a complement of proportion of success. All right, so the requirements are, and we're going to check them every time, is the sample is a simple random sample, and the conditions for the central limit theorem are satisfied. What are the conditions? N times P should be greater or equal to 10, and also N times Q should be greater or equal to 10. That ensures that we have a normal distribution of proportion of success. So we're going to use a normal distribution in order to find our critical values, right? And for that normal distribution, our mean is going to be equal to the proportion of the population, and the standard deviation can be calculated using this formula. P times Q divided by N, everything is square rooted. All right, so how we going to build our confidence interval? The same way we build it for the mean. Only the margin of error will be calculated using this formula. We're gonna, your critical value multiplied by the square root of P hat Q hat divided by the sample size. All right, so let's practice. Let's take a look at some examples. So this is our first example. It says, assume that a sample is used to estimate a population proportion. I think it should say a random sample. Okay, find the margin of error for the sample size of 2107, of which 65% are successes. Use the 90% confidence level. So here's what we have from that problem in short. What we need is we need a Z and we need Q. Well, Q is easy. Q hat, it's 1 minus P hat. Okay, what about Z? Well, we're gonna go into our StuckCrunch, and since we're talking about a 90-degree confidence level, our alpha is 0.1. So in each tail, we're gonna have 0.05. All right, let's figure it out. So I want to emphasize that for critical values to estimate population proportions, we're going to use normal distribution. So we're going to use Z values. Where's our normal distribution? Right here. All right, we're going to use Z values. So the area in the right tail was 0.05. So that Z value is 1.645. That Z of alpha over 2 is actually 1 0.645. So now I'm gonna use that z-value in my margin of error formula. All right, let's go ahead and find the margin of error. So the margin of error is 1.645 multiplied by p hat, which is 0.65, multiplied by q, which is 0.35, divided by n, which is 2107. Let's put it in the calculator. And the value that I got was 0.017 approximately. So my margin of error is 0.017. Now, in order to actually build an interval for proportion, I'm going to use this formula. So again, my point estimate for the population proportion would be the same as the sample proportion, 0.65. But for the interval, is going to be p hat plus or minus the margin of error, which is 0.65 plus or minus 0.017. Okay, so this is one way of writing our interval. Another way is 0.65 minus 0.017 to 0.65 plus 0.017, which will give me 0.633 on the left side of the interval and 0.667 on the right side of the interval. So this is the second way of writing the interval. And then we're going to have, you can also write it as, and using the interval notation, 0.633, comma, 0.667. By the way, this left value, 0.633, is called the lower bound of the interval, and the upper value, 0.667, is called the upper bound of the interval. Let's do one more example. It says construct a 90% confidence interval for a sample with n equals 4,500 and x 2925. So in this example, you're not given the sample proportion, but you're given the number of successes. So you're gonna find the proportion of successes, but by dividing x by n. So that's gonna be 2925 over 4,500, and that equals to 0.65, which gives us a q hat of 0.35. And since we have a 90% confidence interval, it's very similar to our previous problem. We are going to have a same z values, right? So the z is going to be 1.645 as well. what is going to be different is your margin of error, because in the formula we have n there, right? So the z is going to be the same, 1.645, and then times the square root. The p hat, the q hat, everything is going to be the same, 0.65, 0.35. Now the n is going to be different. The n is 4,500, and that will give us a different margin of error. So it's 0.012. All right, so now to figure out the actual interval, we're gonna do p hat minus the margin of error to p hat plus the margin of error. So what do we have? We have a 0.662 on the left, for the left bound, for the lower bound, and oh, I added instead of subtracting. Okay, 0.38 for the lower bound, and 0.662 for the upper. All right, so that's another example.